What is a hash table? Well, hashing is a data structure that in optimal time can provide O of 1 searching, insertion, and deletion of objects. Hash tables use a hash function to break down larger keys into smaller keys that will be stored in the hash table array. The array of the hash table is usually proportionate to the amount of keys that are going to be stored into the array through the hash function. And when the hash function stores multiple keys in the same array cell, then there are different ways that you can solve these collisions, and we'll talk about these later.
Now, this brings us to the history of the hash table. Now, the hash table was first thought of in 1953 in an internal memo at IBM by a creator called Hans Peter Lund. Now, Hans initially created the hash table data storage mechanism in order to more effectively store data at IBM to allow for instant access and rapid search throughout databases. Now, initially, data was stored in buckets, and the storing mechanism that he discussed was most close to hashing with a chaining collision handling. Now, just a year later, linear probing was actually created, and the creator was either Amda Hall or Hirschhoff, as there were two creators at roughly the same time. All right, now that we've talked about the history of the hash table, let's talk more about the actual solution. Now, a hash table involves using an array to store values at a unique and dispersed location throughout the array. This means that since items will always have a unique or roughly unique address, there will be O1 access, insertion, and deletion because you always know where things are stored. In order to figure out where things are stored, we utilize a hash function. Now, the goal of the hash function is to give everything a unique address or index at which you're going to store the item, so as to roughly disperse items throughout the array. Now, there are three common types of hash functions. Firstly, the most common is simply using modulus. So you receive an item and then, for instance, a student, and you can hash their student ID, for instance, using modulus with the length of the array to derive directly an index at which the student object will be stored, or through using modulus with a prime number. Modulus with a prime number is more effective as utilizing a prime number prevents frequent collisions or when items are attempted to be stored in the same places. It's best if this prime number is roughly the size of n. However, the issue with this is if you use modulus with a prime number, you'll also have to do modulus again to get a direct index, because the prime number and the length of the array will probably not directly coincide. Now, an alternative to that is called bit masking or reduction. This is very useful if you have strongly numerical data types. And what you can do is, for instance, for a student ID, you can drop the first 16 bytes and use the last 16 as a memory address. If everyone has a unique student ID, then this is incredibly effective as it's a zero collision solution. An additional alternative is called the universal hash function. Now, a universal hash function actually utilizes several different types of hash functions, and its advantages for complex data storage. If you have several different types of classes that you're attempting to store, then you can use a different type of hash function on each and every one of them in order to roughly store them in different places and prevent a lot of collisions. Now, as we discussed, collisions are still naturally going to happen because data is not completely unique. So there is going to be some overlap where some items receive the same hash value. In order to handle that, we have two different types of mechanisms of collision handling. They're called separate chaining and open addressing. Now, separate chaining is a mechanism in which all items that are hashed will be stored at the memory address. However, it's very likely that at the memory address, you will store a larger data type, which will include all the single items that are being stored. So let's give an example. For instance, you could use a linked list to chain the items. So the first item, for instance, on the top right here, John Smith, receives a hash of 152. So at memory location 152, you create a linked list with one node, John Smith. Now, moving on, we insert more values, and then we get to Sandra D. Sandra D also has a hash that is 152, right? So what that means is you're not going to look for a different memory location, but you actually add the student as a new node to the linked list. So this means that with separate chaining, you're always going to be storing your items at the memory address in question. There are different ways to store them. However, they all require complex data types. So you could use a linked list, but the issue is since you're adding to the end of the linked list, you may have to navigate all the way to the end for instance, like searching or insertion. An alternative is the self-balancing BST. This is very useful if, again, you have some numerical data types that follow a pattern. And for instance, you could create a heap. And then as opposed to having an O of N search through the linked list, you could have an O log N search because you could follow a certain pattern to navigate, say, the min heap or the max heap. Another alternative is the dynamic array, which functions very similarly to a linked list, but has the advantage that in cache-heavy problems and solutions, you would be able to store all your values at contiguous memory locations as it's an array. And so there would be a quicker search through this data type. Now, the alternative to separate chaining is called open addressing. Open addressing involves not storing complex data structures at memory addresses in the hash table, but actually storing the values at these locations. So in open addressing, if a location is taken, but you receive the hash that tells you to store at this location, you actually go to the next available empty memory address and just store at that place. However, the thing is there's different ways, different intervals that are used to prevent clustering, or when a lot of things are hashed and stored in the same places. There's different mechanisms in order to disperse things more evenly. So the most simple open addressing solution is called linear probing. In this one, for instance, John Smith is hashed to 152. You simply take a fixed interval, in this case 1, take one step, look at that memory location, and if it's open, fill it. So Sandra D, instead of 152, stored at the next available spot, 153. So this fixed interval can change, and it could be any amount of indices. An alternative to this, though, that will prevent an incredibly large amount of clusters stored at one spot would be quadratic probing. In quadratic probing, you would actually take different steps with every collision. So for instance, if you have a collision at your first location, you take one step to the next one. If there's a collision there, you take 2 steps to the next one, and then 4, and then 8, and 16, and so on, making sure that your data becomes more dispersed if there's more collisions. Another alternative is called double hashing. Double hashing actually creates a unique step for each data item, which could be very useful because, for instance, you use a person's ID to derive their memory address, the index that they should be stored at in the table. And then you can hash their, say, birthday to get the steps that you should be taking to find the next available address. Now we will talk more about the advantages and disadvantages of each later on. But as you can see from the graph on the right, in general, linear probing is best when there's this lower load factor, meaning that the hash table is largely empty, at least half or so, and there's not significant clustering. If so, there's always O of 1 access because you can get directly to the data item without having to navigate a linked list. However, if the data hash table, becomes extremely filled, then chaining becomes more effective because with linear probing, you would always have to be taking very many steps to find the correct address, while a linked list would not store all of your items at this location. Now, let's try an example.
All right, now here we have our first example of the hash table data structure. So in this data structure, we have an array of cells with memory locations and information stored at these addresses. Additionally, they have indices that are attached to the memory location in the array. Now, this data structure also includes a hash function, which will be used to help figure out an index at which all of these items will be stored. Now, for the current example, we're going to access, store, and delete certain items in this data structure. And the specific hash table that we have here uses a hash function with a prime number modulus, and additionally uses chaining for collision handling. Now, my colleague Justin Park here will take you through some examples.
All right, so now we're going to be inserting Bobby into the school directory using his ID. We're going to take Bobby's ID, which is 35, and send it into the hash function. So we have 35 mod 37, and that's going to just stay 35. And then we're going to take this hash value and mod it by the length of the array in order to fit the hash value into the index. So we have 35 mod 12, and that's going to equal 11. So this is the index that we're going to put Bobby into our hash table. So Bobby will fit right here. And then we're going to insert Paul into the hash table, and his ID is 69. So take 69 mod 37. That'll give us 32. And then we're going to take this hash value, put it into this mod 12. And that'll give us an 8. So in this case, when we're adding Paul into the directory, we already have a couple values that are in that index. So we're going to add Paul to the end of the linked list that is stored into this index 8 cell. So here we're going to add Paul at the end. And then move on to the next student. We have Kaylee here, who has an ID of 52. So using the same process, just erase this. 52 mod 37 can equal 15. And then 15 mod 12 equal to 30. Once again, there's already a value inside the index that Kaylee needs to fit into, so Kaylee will be added to the end of the linked list that is in that cell. And then finally, we have Umami, who has an ID of 103. So put that into the hash function. And 103 mod 37 is 29. And then we'll put this into the index calculator. We'll get you 5. There's nobody in index 5, so we'll just insert Umami right into here. Okay. Okay, so now we're going to be looking into searching for an ID of somebody who's already in the school directory. So we're going to search for ID 74, and it's the same process as inserting, where we have to send the value of the ID into the hash function and into the index calculator in order to search the linked list to find the student who has that ID. So we're going to take 74 mod 37. And this will just give you a hash value of 0, and 0 mod 12 is going to be 0. So after we get the hash value, which is 0, and we know that 0 mod anything is going to be 0, we go to that index in the hash table and see that Mario is the one that has the same ID as that we're searching for. And then we can go to the next item, which is ID 53. 53 mod 37 is going to be equal to 16, and then 16 mod 12 will get you 4. So once we have the index here, we look through the index that matches in the hash table, and there is only one item there, so we find out that Snake matches the ID of 53. and just return that object. And finally, we're going to go through deleting. Deleting works in the same way as searching and inserting, where we take the ID value, put it into the hash function. So 57 mod 37 will be 20, and then 20 mod 12 will get you 8. So we go to the 8th index, and in this case, this index has a linked list with 3 different people inside. We search for whoever matches the ID 57, and in this case, it'll be MinMin. So we'll delete MinMin from this linked list, and everyone that proceeds will have to be pushed back 1. So now we'll have Peach inside here, and Paul inside after.
So here are some advantages and disadvantages of chaining. Starting with advantages, first off, it's simple to implement. It is an array where each cell has a linked list, and every time that a collision occurs, you throw in the new object in that cell's linked list at the end of the linked list. And hash tables also never get full because you're just appending to the linked list instead of sending each object to different cells of the array. And most of the times you use chaining when you don't know how many keys that you need to insert, because if you insert too many and you're not using chaining, then for instance, for like linear probing, you're adding the new object into different cells of the array, and eventually you might run out of space and have to create a new array in order to copy down the values with more space in that new array. Some disadvantages are that it wastes a lot of space because there are cells in the hash table that you will just never use sometimes. And when collisions occur too much and there are a lot of items in a linked list, then the searching and deletion, they become O of n time in worst case. And there's extra space used with links that come from the linked lists in each cell.
And now I will switch over to my colleague who will go over linear probing.
Thank you. All right. Now, so we just discussed collision handling using chaining. However, the big difference with linear probing is, as we discussed in the past, you don't use linked lists at the addresses, but instead you actually store the item that is stored at this address. So in this case, all these students are having their object stored at the memory location pertaining to their address, which we'll find through the hash function and the index. This will lead to interesting situations when collisions arise. So, going back to our examples, first of all, let's insert Bobby. So Bobby, apply the ID to the hash function, we get a hash of 35. And then we mod that result to get an index value of 11. So that means Bobby needs to be inserted at the 11th index in this array. Now, as we can see, there's empty space right there, so we can successfully insert the student. Moving on, Paul, ID 69. So we hash that, 69 mod 37 to get, I believe, 32. Now, mod the hash value produced by the length of the array to produce the index. Index is 8. And as we can tell, that memory location is open. We successfully insert Paul. Now here's where things get more complicated. When we insert Kaylee, we hash her ID to get a hash value of 15. which produces an index value of 3. Now, as you can see here, the third index, or the fourth index, but index 3, is actually full. So that means we have to here engage linear probing. Now, there are several types of probing, for instance, quadratic probing, or using a multiple hash implementation, where it comes down to, if a memory location is taken, how do you decide what the next one is? So in this context, we're going to apply the simplest formula, which is just linear probing. So you keep on accessing the next memory location until you find the right one. So in this case, 3 is full, we go to 4, 4 is full, we go to 5, and then we insert at 5 in the next open memory location. So the difficulty that arises with this solution is, for instance, as we can see, we already have 3 solutions in a row. And if we tried to access Kaylee earlier on, we would have to search through 3 items. Now, if this list got incredibly packed, then you would have to be potentially searching through a lot of items for every access, insertion, and deletion, creating an actually O of n worst case solution. Next insertion, let's insert umami. So, ID hash 103 produces a hash value of 29. Now, we mod that hash value to get an index of 5. Now, as you notice, there are some collisions there. So, we take the index value of 5. As you can see, index value of 5 is taken, and we go to the next one using linear probing. So index value 6 is open, and we successfully insert at that location. However, as you can tell, even now, our array is only roughly 3/4 full. But still, there are already a lot of collisions because they often happen in clusters. And due to this, that means that, for instance, an access operation can take significant processing and O of n time. For instance, if I want to insert something at index 3, it would actually be inserted at index 9. Now, this carries us over to the advantages and disadvantages of different methods.
All right, now that we have shown an example of linear probing collision handling, let us discuss the advantages and disadvantages of linear probing and open addressing in general. Now, the advantages of this collision handling mechanism is that it actually uses all empty memory locations. So in the hash table, if there's an empty memory location, at some point through open addressing, the interval will align in order to select this item and place a value at that location. So as such, because all values in the hash table are being used, that means less memory is being used overall. Additionally, since you're not storing complex data types like linked lists and binary search trees at these indexes, there's also less memory use due to not having as many complex structures. So as such, linear probing and open addressing is very effective when the table is not full. So for instance, when half the table is filled and there are no significant clusters, then you will always have O of 1 access, insertion, and deletion. Because maximum, you're only going to have to take a couple steps in order to find the value that you're looking for. And you're not going to have to store these complex types. Now, the disadvantages of linear probing, they really arise when there's a significant amount of clustering or when the data, when the hash table is nearly filled. Because when there's a large amount of clustering in a very packed hash table, then after attempting to insert or access something at a location, you're actually going to have to take very many steps in order to locate its actual memory address. Now, this will effectively mean that you're doing an exhaustive search of the array, giving you O of n time for your operations. So as such, open addressing is most useful when you have, for instance, half your values filled in the hash table. Now, additionally, hash tables with open addressing, they can only hold a finite amount of data items. Because if you have n data items and you attempt to add n plus 1 item, then your entire hash table array will actually need to be resized in order to make it larger to support more values. However, the additional issue with this is you're actually going to have to rehash all your values in order to get the correct memory location at which the values will be stored. So this is very costly, and that means that hash tables with linear probing should only really be used when you know your data set and you can make the hash table large enough to not create a massive amount of collisions and clusters.
All right, so the basic insertion, removal, and accessing for a hash table has usually a time complexity of O of 1 time, but collisions do make this average case of O of 1 to O of n worst case. And the way it works with chaining is when there are a bunch of collisions in the chaining, then a linked list will have a bunch of items in one cell. And then when you try to access, like delete or search for an item that's in that linked list, you may have to search through the whole linked list, which makes it O of n time. For linear probing, collisions affect the insertion and searching and deleting, because when there are way too many collisions, then when your hash function gives you the index that you need to put the object in, that might already be filled and you'll have to go to the next available space. But this process may take a long time because each index that you want to go to might have something in it until eventually you might get to an open space. And when you want to then find that item, you're going to have to go through the hash function and start at where you were supposed to insert that item and then trace your way all the way to where your item is at the end. And another problem is that with linear probing, you may fill up the entire size of the array in your hash table, and then when you try to insert another item, you'll have to rehash that table into a bigger table, which takes a lot more time. So there are many different applications to hash tables in many different algorithms, and some of these include password verification, the Rabin-Karp algorithm, message digest, and connecting file name and path. And all of these use hash tables in order to store information in a hash table with certain information from each of their respective algorithms.